Do, 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 do. Good morning. Just loading up slides here. Another minute. Sorry, I should have had these loaded in advance. Forgot all about loading them. Almost there. Here we go. And where are they? It is. Okay, we can present. So, morning, folks. Hope you enjoyed the snow yesterday. Steve sent this one along. Steve's the one that sent us the view last class from his patio on Kearney Lake. He sent another one yesterday afternoon uh, showing what it looked like there. You got a lot more snow in Halifax than we did down here. We've got some, but really not much, and it's melting now. But I understand in Halifax you had about 10 centimeters. That's quite a bit for the beginning of November. Uh, for those of you in Barbados or China or elsewhere, just look at what you're missing. Anyway, so uh, I thought this was actually a couple days ago. So this is what Kingsburg looks like uh, as you drive down the road out to this village. It's about a 5 to 10 minute drive to get there, and then you come crest over this hill, and you look out. You've got the ocean down below you. There's a little pond here, and that's the community down below. Um, I live off to the left of this picture. And just a second. Sorry. See, you may be able to see that little sign to the right, which says Hurdles Beach Road, which is where most of the traffic goes because everyone's going after Hurdles Beach with the big waves. I got a couple pictures of those from just the other day on the weekend, I think it was, and share them with you another time. So on with today. Um, so today we're going to start in on probability. That and so last day we were looking at classification, and generally we're trying to fit things into two groups, sometimes into more than two, but two is far and away the most common. And there are many different approaches. We can build a formula to estimate a probability. We could build a formula or a rule for separating two groups, a discriminant function type of thing. We could do it by looking for similar cases. That's what KNN was all about. There are lots of different strategies. Yes, Giselle, test is this Friday. And I'll speak to that in just a second. And there are several methods that you may want to try. You may want to use them all. If you do that route, then you should take your data set and split it into two groups. One of them to do the training to fit your model and decide what the formula should be or what have you. And then have a separate test set that every method then gets applied to see which one works best on this set of data that you've not experimented with. And but we'll talk about that when we get to evaluation. So today, most classification strategies involve finding a probability that a huge proportion of them do. All of them make some errors in misclassification. And so we have to evaluate the chance of error. It's a probability of an error. And it really is important to have some basic understanding of probability to understand classification and the evaluation of classification models. And some of you may have been exposed to this in high school or in other courses. We'll just spend 2 classes going over the basics and some of the jargon and the like, because if you're reading other pieces, you'll encounter the jargon and how to figure that stuff out. Giselle, about the test Friday, and that's only 2 days away. Um, I'm struggling making up questions at the moment. The material that we've got um, that you had on chapters 7 and 8, that is it 7 and 8 on the test? Or is it? Yeah, I think. I'm losing track. Um, that um, they're awkward ones in terms of posing good questions. And if you look at the quizzes that were there for those 2 chapters, um, the questions weren't all necessarily the best job of questioning on it. And I'll have, and I covered off pretty much everything I could ask questions on those 2 chapters in the quizzes. So it's coming up with new ideas is maybe awkward. So I may be covering the same stuff, asking similar questions, um, but maybe reword the responses slightly. I think I'll probably draw heavily on those quizzes as examples to use. I don't want to surprise you with something that you really didn't see. So um, my recommendations in reviewing for the quiz, uh, I'll be probably focusing on what was asked in those 2 quizzes and trying to keep within those sorts of boundaries. The only other material to review, I wouldn't reread the chapters, uh, that because there's different things I've emphasized in the classes possibly than in the chapters. And so I think I would, if I was going to ask anything a little bit different, it would be by looking at the 4 lectures that we've had on chapter 7 and 8. And so look at those ones as examples that you may be able to draw from to come up with ideas for what I might ask. So look at the lectures as opposed to the chapters, and look at those last 2 quizzes. I'm still struggling to get a test devised that everybody does well on, and that's still my goal. Um, I um, I've not been very successful so far, but I'm going to be trying again. Um, don't worry. I'll fix things. I'll adjust grades, whatever, if it doesn't come out. Probability we hear a lot about, that, what's the chance of different things happening? And the uh, uh, leading up to yesterday, it was, what's the chance that uh, Trump would win the election? And the website that I follow, I've mentioned before, 538, um, it gave Trump about a 1 in 10 chance of winning the presidency. It's still on the edge at the moment. Um, they, uh, their feeling was that uh, Trump really had a chance, but and if it got to be close, because there's several states and the way it does in terms of that electoral college, it's not just popular vote. If it was popular vote, it was relatively straightforward. Biden would win. But because of the way the president is elected in the US, it's a very complicated system of winning different states, and you get so many votes for each state you win. Um, if you look at it, a large number of states, it's a very, very close race. So all you need is just a change slightly in the percentages to flip things around. So all these different forecasts of the chance of this, the chance of that. Um, uh, Now we're seeing what's the actual thing that happens. And this is relevant. Um, I can't show you this easily with my little picture here, but the easiest example of probability is flipping a coin. So I've forgot to bring a coin with me in here, but if I was to go and flip a coin, and a Canadian coin has generally got the queen on one side and an animal or something on the other side. If I flip a coin and then catch it, put it on my hand, what's the chance that the queen's image is facing up? Many of you, I think, would say 50%. That, you know, 50-50 chance. It could be the queen, it could be a caribou, it could be the queen, it could be, I'm trying to think of what's on other coins. A caribou's on a quarter. Um, oh, well, the blue nose is on the dime on the other side, but a dime is too small. I'd probably drop it. But I think you'd agree that if I flip a coin, the chance the queen's face is facing up is 50%. That, and how did you get that? Where did that probability come from? Because probability is the number. How does it come from? And you probably thought that it was a fair coin. You couldn't see my coin. You couldn't see if I had a trick coin or something, but you're assuming I've got a regular coin like we would get. We're all paying with debit cards now because of COVID, but when we used real money, when we were buying things, we had coins. And if you're assuming I've just got a regular coin, then queen's one side, something's on the other side. So it should be 1 out of 2, right? And I've got no special technique. You've got a theory. And so we would call that a theoretical probability. And if you're talking about probabilities to do with gambling, with lotteries, with playing cards, with roulette, with a lot of those sorts of gambling situations, that not sports betting, not horse race betting, and that type of thing, but if it's on uh, things you'd see at a casino that were gambling things, we can work out the probability of various events happening based upon a theory. And presuming that that the dice we have are not fixed in some fashion or that the deck of cards is not arranged in some special fashion. I should mention, though, if I flipped a coin, caught it, put it on my hand, and asked you, is the queen's face looking up? What do you think the chance is that the queen's face is looking up? So imagine I've got my coin. I don't have one now, but suppose I've got one there. In chat, what would you give as an answer? Any thoughts? Anybody typing? Gisela, you're the only one out there? Oh, nope, Esther is, I think. Maybe. Oh, you'd think it's 1 out of 2. You'd think it's 50%. Almost everybody I ask will give me that answer. But the trouble is, you say it's a 50% chance the queen's looking at me, but I can look down and see the answer. And my answer is either right or wrong. How can you have one answer and I can have another answer to the same question? How does that work? And it's because it's sort of a trick question in some respects. If you look at what I've said here on my slide, I underlined it. It's a future event. Probability has to do with the future. We can't talk about probability about the past. And after I caught it, put it on my hand, it's now the past. And so past things, like if you were asking, what's the chance, I'll ask you in a minute, chance of you doing well on the test on Friday. Uh, you could talk about that, but after you've written the test, you either did well or you didn't do well. You got the right answer or you got the wrong answer. There's no more chance involved. And we've got to think about those sorts of things because probability generally talks about future events or hypothetical events. We shouldn't be using it generally to talk about past events. And many times people ask, well, what's the chance you made the right decision? And maybe I don't know if I made the right decision or not. Um, that a lot of issues that come up in statistics and misinterpretation of things in statistics has to do with people talking about the chance their decision was right or wrong. Their decision was right or wrong. The probability is 0 or 1. You just don't know which one it is. So suppose the test on 20 is, or on Friday is out of 20. It's probably not going to be out of 20. But it'll probably be 18 again. Um, so, but if it was at a 20, what's the chance you will get a score on Friday that's 16 out of 20? And you may come up with some number. You have some gut feel about the chance you're going to do well on the test, or maybe you haven't done well on past tests and you're going to say it's a low probability you're going to do well because the, your past experience has been negative. Um, it's your opinion, it's subjective. And there are an awful lot of cases where an expert is asked, what's the chance of an oil spill? What's the chance of, certain calamities happening in the future? What's the chance the stock markets are going to go down by the end of today? Yesterday the stock markets were going up. In large measure, I think that people were feeling the election is going to be predictable. Biden's going to win. Okay. They may have wanted Trump to win or whatever. They may think Trump might be good for the economy, but they thought it would be all resolved today. And that the markets like certainty. They don't like uncertainty. Um, so the markets went up a lot yesterday. This morning the markets are still going up, which surprised me because there is so much uncertainty right now about who is going to be the president of the U.S. that uh, generally that should drive uncertainty, risk drives the markets down. But people might talk about the chance of different things happening, and if it's based upon their experience, we call that a subjective probability. And they're common. It's what we ask experts to tell us about the risks that we're taking with a new investment of building a high rise in Halifax. That what's the rental market going to look like? What's the chance it's going to keep booming? What's the chance it's going to go down? And uh, we use this a lot in scenario planning. And we're not looking for precision in the estimates of the probability. We're just trying to look at, is this something very likely to happen, somewhat likely, or very unlikely? And then we build different scenarios. So governments around the world have been building scenarios based upon Biden winning the election, Trump winning the election, it being like we have right now, uncertain who won the election. And they may have assigned probabilities to this, but they built these different scenarios and they tried to use that in their thinking over probably the last 2 months in terms of their relationship with the US. Um, and it's useful to get your head around things that what are things that are likely to happen. There's a high probability you think and you should plan for, and things that you think are very unlikely to happen, and how much you should invest in planning for those unlikely events. Um, that what we're going to look at is a different set of probabilities. So I took the survey that you completed, and the one from last fall, and the one from last winter, and I've combined the questions about how often you worry about your grades and how often you feel depressed. And that those two questions were on all three surveys. And so I've got more data by putting them all together. You may argue that things have changed and depression has changed. And there are three very different groups. Students who take courses in the winter are different from you. Uh, they're more likely to be brand new students directly out of high school. Um, Different mix altogether. But anyway, let's throw them all together. And we might ask, do many students worry about grades? Do many students experience depression? Do they experience either one, worrying about grades or depression, or both of those sorts of things? As grade anxiety and depression, are they related to each other? Meaning, like, do those who experience depression worry more about their grades? Do those that don't worry about grades, do they experience less depression? That, can we find any patterns that are within that type of thing? And the way we'll look at those patterns is by looking at probabilities. And so here's a table of those numbers, and I squished the categories down so that we'd have lots of students in each box in my table. I didn't want any boxes with just 4 or 10 or something like that. So with depression, I grouped it into rarely or every few months as being not depressed. And those that experience it several times per month or several times a week, I viewed them as people that they're depressed often. And then once per month is sort of on the edge. And there's a good sized group that put themselves on the edge. And worrying about their grades, they're ones that basically all the time or often, I called them worry. Those that sometimes worry or rarely worry, I put into the don't worry group. And so I could get some groups of similar sizes here. This table of frequencies that I've got in my table is when you take statistics, they'll call it a contingency table. It's a table that summarizes every type of a combination of those students, okay? And so all the students that responded to both questions, there were 583, and this is how they all fit together. And so let's start out and ask, how often is depression? So what proportion of students say they're often depressed? And we're just analyzing the data just like you did some stuff similar to this in your last assignment, or assignment before the second assignment, I guess. And so if you look at that table, there were 207 that said they were depressed. I've got 583 students. So I could say that 36% said they were depressed several times per month or more often than that. Okay? That's just a proportion from a sample. But if I turn it around and try to use this to generalize, if I put it in an article and publicize this, and said that 36% of students experience depression frequently, well, now I'm generalizing. And so if we assume that future students that are similar to what we've seen in this course in the last 2 years, maybe I'm going to say in the future of students taking this course in 2021, whether it be in the fall or the winter, what's the chance that of a randomly selected student I choose that they're frequently depressed? Would that be 36%? And this isn't, I don't have a theory here. I don't have a theory about depression. It's not like flipping a coin. It's not purely subjective. It's based upon experience, but I've got hard data that measures this. So generally, we don't call this a subjective probability. We call it a relative frequency probability. It's based upon a sample. It's just an estimate. It's not perfect. But it's a relative frequency, like we've had relative frequency before, where you change a frequency and make it as a percentage. And that's all it is right now. But we use these all the time. This is the most frequent type of probability that organizations work with. That it's an estimate, so it's not going to be perfect. If I had a bigger sample, I'd get a better estimate. Let's just assume that my numbers are exact, okay? And or you could, if I said it was exact, then I could then talk about probabilities of future students. If I want to phrase it in the context of what's the chance I grab one student out of that group of 583 what's the chance I grab a student that's frequently depressed? And say that that 583 might be representative. And when I'm doing it out of that group and just talking about it, it is an exact probability because I'm not generalizing about all students. It's no longer an estimate. Okay? It's an exact probability. But if I was generalizing to students in general, it's just an estimate of that probability. Subtle distinction, but one to keep in mind because we know that our numbers are, if it comes from a sample, it's not perfect. And so there were lots of estimates of probabilities to do with the US election, and they're from opinion polls. They all had margins of error, and there's a lot of distrust in polls at the moment. There was distrust after the 2016 election because the results turned out to be different than anticipated. But actually, they were Trump winning in 2016 was in the margin of error of those probabilities. So if it was 36% plus or minus 3 percentage points in this case, in his instance, if you move 3 or 4 percentage points either way, if you had that happen in a couple of states, Trump won. And it wasn't impossible to happen. It was less likely, but it was within the margin of error. And it may be that that's what we're going to have with this one, although the feeling had been that the gap between the two was big enough that he wouldn't win even if you were at the extreme of the margin of error. But still questions about polls. Anyway, relative frequency probabilities, they're the most common we see in business, that they generally describe our risk in decision making. They're based upon the data that we've got, and the data may not be valid. If it's historical data, it may be the past doesn't predict the future. If it's survey data, it may be that people didn't do what they said they were going to do, like in those opinion polls. Uh, Maybe they said they would vote for Biden, but they were just too embarrassed to say that they were going to vote for Trump. That was believed that some of them were lying. Others may have decided, Biden's so far ahead, I don't need to vote. And the Trump supporters all went out and voted, and the Biden supporters didn't. That has been criticism that Republicans are more likely to vote than Democrats. And so they're not perfect, okay, but they are our best guess because it's the only data we've got. Understanding risk is really important to understanding your decision making. And most of us don't understand it very well. As we work through probability, maybe your understanding will improve a little bit, but it'll still be a foreign idea. It's not something that, it's like with this election. Once the election was held, Trump wins or Biden wins. It's either or. All that risk, that probability disappears. And so when we're told about the chance of rain, it ends up raining or it doesn't rain. It doesn't 70% rain. It's either rain or it isn't. Um, so we have difficulty in wrapping our head around it. And even when we understand it, we're not necessarily rational in the way we do that. And I'll come to that a little bit when we do evaluation, just briefly. But we have a difficult time dealing with um, probabilities that will view a risk as being high in one case, and then the same probability will view as not being high in another case. So back to my data that I had here. So just a bit of notation, and I'm going to start introducing jargon here, and a lot of jargon today. That let me, it's at times difficult to write out everything with words, and so we frequently will use symbols. Pick symbols that make sense to you. Um, so if I'm looking at depression, I might use D to represent depressed. Generally, the letter P stands for probability. So I might write P bracket D, this thing over here, as representing the probability a student is depressed. And that my 36% I had before. We talk of an event happening, and this is a common piece of language, the chance of an event occurring. And so what's the event? The event is randomly selecting a student who's depressed. Okay, so depressed is that event. That if I asked what's the chance that a randomly selected student worries about their grades and is depressed, is two things. It's a combination. We call that a joint event because it involves multiple things. So just to make you aware of certain pieces of language that I'll try not to use the language too much within the course, but you're likely to encounter different things to do with probability as you go through your program and afterwards. And this is the probability speak, their language that they use. So when I'm talking about two things, that they're and, that's viewed as being intersection. It's the crossing of two things. So if it was, I can't highlight this on my slide, but I'm looking at being worried. So I'm looking at being in this column, and I'm being depressed in this row. So you could think of it as the intersection of this column and that row. And some of you may have learned about probability with Venn diagrams, and I don't use those. I just look at my table and I talk about where they intersect on my table. So this column intersecting with that row, there's 151 students. If I'm looking out of all the students that I'm picking this one, that's out of 583. So there's a 26% of the students in the survey were both worried students and depressed students. They had both of those characteristics. You'll notice that I am rounding things to 2 decimal points. I always do, almost always. If I told you the chance of a student being depressed was 36% or 30% or 40%, you'd probably view all those numbers as roughly the same. You can't distinguish between them. It's sort of a moderate, it's not a really low probability like 5% or 10%, and it's not a really high probability like 70 or 80 or 90%. It's below 50, but differentiating between 36 and 30 and 40, you may have trouble doing that. So if I told you it was 36.14, doesn't give you any more information, but those extra digits make you have to think harder. It's a lot of clutter for you. And when we did pivot tables and that sort of thing, I said, get rid of the clutter. People, we use too much precision or show too much precision when it really doesn't make sense to. We don't need it. Exceptions to that, if the probability turned out to be 0.0026, that's would be 0.0026. So I've chopped it over 2 decimal places. That's like 26 in 10,000. So that's very infrequent. When I've got some leading zeros, yes, I show them. Okay, and I'd say that's 0.26%. That would give me 2 digits. Or if you're showing the decimal, you show the leading zeros, the zeros that come right after the decimal point, until you get 2 real numbers, but don't go beyond 2 real numbers. And also remember, it's an estimate. My 36% or this 26% is just based upon 583 students. So I know it's probably off by 3 to 4 percentage points either way, because I can't estimate that accurately. When writing it out, I've written with that special symbol, that upside down U for intersection. I rarely ever use that. I like using the word and, because then I know what I'm saying, worry and depressed. And I'll even write it out in words like I've written it out here, because then I know what I'm saying. That, and sometimes if I'm using symbols, I just write the 2 letters together, WD. Anybody that sees that will think, oh, that's worried and depressed. And so keep it simple. Putting in that intersection sign, for many people, it just scares them off. It confuses them. So again, think of how you'd communicate this to someone else. How do you communicate it to yourself? How do you absorb information? Another piece of jargon. What if I said, what's the chance a student did not worry? How do we write that? Well, not worry. Usually what we do, if you're saying just the opposite of something, worry, not worry, then I'd put a W with a little tick mark above it. And that would be my way of writing that type of thing. And that's, you can see on my table here. Now, with depression, I had depressed, not depressed, or once a month. So I wrote those out as three different things. And I just sort of picked letters, numbers in this case as well, to remind me what it meant. And you can make up anything you want. There's no magic uh, strategy for doing that type of thing. But remember, if I asked you what proportion are not depressed, 36% are depressed, then 64% are not depressed, one or the other. But the not would actually represent these two groups together. It's the opposite of depressed. So it's making things in a binary fashion, yes and no. So watch out. Sometimes that complement could actually include several other different types of cases. And we get a rule with this. So if I've got 60%, in this one here, I've got what percentage worry, 60% worry, 40% do not. If I add together the proportion that worry and those that don't worry, I have to get 100%. So either you're worried, you're not worried, those probabilities have to add to 1. And sometimes we will do problems, not in this class, but you might in another course, want to write a probability in a different fashion. Let's see, if I gave you the probability that something simple, well, a common case that we get is doing what we call inspection sampling. We get a shipment in from the supplier that we want to go and check to see if they're any good, if there are any problems with the shipment we received. We can't inspect every possible unit, tear apart every box and pull out every unit and test them out. So maybe I go and take out 20 units. And my decision rule is that if I find 2 or more units in that box that are defective, that there's something wrong with it, then I tell the supplier I'm not going to accept it. And I can work out under certain conditions what's the chance I get 2 or 3 or 4 or 5 or 6 or 7 defectives all the way up to 20. And it's a lot of work to work out the probability of 2, then I have to work out the probability of 3, of 4, of 5, of 6, all the way to 20. There's 18 calculations I'll have to make. An easier way to calculate that would be to say, what's the chance I get 20 that are perfect? What's the chance I get exactly one that's defective? Add those two together, and they'll represent 1 minus the probability I get 2 or more. Because I've got to be, the number I get defective has to be 0, 1, 2, up to 20. Has to be one of those numbers. And so the opposite of 2 and above is 0 or 1. So it's less work. So occasionally we use these rules to simplify things if the complement is simpler than the thing I'm studying. But that's a piece of jargon we use. What else do we have? Oh, another one. I did before worried and depressed. What about worried or depressed? That one, with sets and Venn diagrams and thing is called union. And so that represents being in the worried column or the depressed row. Okay? So it's this column or that row, not and. And so you could just add them up. 121, 78, 151, and 56. Divide it all by 583. You get your answer out. You get 70%. Good. That I've just added up all the cases that fit that description. Everybody in that column, in that row. Don't include the totals because that'd be double counting stuff. But also look, I could take these 350, these 207. These are all the worried students. These are all of the depressed students. And if I take those two totals, I'm going to double count the 151 because it's in this column and it's in that row. So I've got to take them out. So that's what I did here. I'll get the same answer. Yeah, I should. Okay. Just thinking about that, though, gives me a rule. So this is worried or depressed. I take all the worried students, all the depressed ones, subtract off the ones that I've counted twice, divide by 583. That's how I work out the 70%. But let me divide each thing by 583. And that's okay to do. You can do that type of division. I've got this one, this one, this one. These three things are all probabilities. This is the chance of a student being worried. This is the chance of a student being depressed. This is the chance of a student being worried and depressed. And so this or relationship as a formula ends up the chance of the first thing, chance of the second, minus the chance of both. So you have to be careful when doing it. And with the table, I hope you could see the logic of that. That what sometimes we would see people do is say worried or depressed. So you're worried, you're depressed, or you're both worried and depressed. And you'd want to add all three things together. No, you're double, triple counting those worried, depressed people because it's the worried and depressed are here, they're in this number here, and so I have to take them one of those cases away. But this we think of as our addition rule for probability. Some other stuff in terms of the language, and that's what I'm doing today is just language, the jargon that we use. Okay, that and thinking of the different ways I could phrase things. What's the probability that a depressed student worries about grades? This phrase, if you don't read the stuff I've got down below it, confuses many people. That I probably should have set the slide up so I pose the question and then give it on a separate slide. Try to fix that for the next class. That if you don't read what I've got there, what would be things that would come to mind of the probability that a depressed student worries about grades? Anybody want to try typing anything? They're just that their thoughts are. Since you've already read the answer, you probably know what the answer is. No one's typing. In this thing, the language is really important because it tells you at the very beginning that the student is depressed. That's known for sure. Okay, we're only looking at the depressed students. And then we're asking among that group who worries, how many of them worry. Well, I've got 207 depressed students. I don't care about these other ones up above. And 151 of them worry. So that probability is 151 out of 207, or 73%. So 73% of depressed students worry. It's higher than what we had among the general student population. To do that symbolically, I write it worry given depressed or worried among the depressed. That and in that sort of sequence. So worried is the thing I don't know, the thing that is I'm trying to find a probability about. And then one on the other side is stuff that I know. So I'm separating them that way. And so the one on the left is what we're trying to predict. Think of it like a formula. Usually with a formula, the thing on the left is what we're trying to predict. The thing on the right is the thing we know. That the so it's like even a formula y equals mx plus b. X is what you know, and you're trying to get y. And so it's in that same sequence. Some students actually go and think of this if they're given a table like this, that as division. I'll take the W's and divide by the D's. I take the 151 and I divide by the 207. So they think of it as dividing, and that's what we did. So there are sometimes different ways of trying to remember, how do I do this? That particularly when if you're in a test situation, you don't necessarily think through things. So yeah, it's the 151 out of 207 is the answer that we've got. So if I asked you, among students that worry a lot, what proportion are depressed? So the general student population, we said 36% are depressed. If we are only looking at those that worry, what proportion are depressed? So among those that are worried, what proportion are depressed? Anyone want to take a crack at that? I know I haven't written it out. Hopefully you heard what I said. Danny's typing, I think. Maybe not. Nothing's popping up here. So among the worried students, what proportion are depressed? Nobody wants to take a crack at it. So these are the worried students. I don't care about these ones. I can close my eyes and ignore them. They don't apply. That I'm only looking at these ones. So I've got and various people. It shows to me that someone's typing, but I'm not getting answers out. That now a whole bunch. So you're taking 151 out of 350. So that's the worried students. So it's not the 233. They shouldn't be part of my problem because they're not worried. And it's the 151 that are depressed. And so that ends up being, oops, I'm going to come back to this. So this one here, I'm going to do depressed given worried. It's the 151 out of the 350. So let me flick back and just show you something again with those numbers and playing with them. I like to play with numbers. They worried given depressed. So that 70% I was working with before, these were the number that were worried among those that were depressed. And if I divided top and bottom by 583, which you're allowed to do, dividing both top and bottom by the same thing, this number on the top would be worried and depressed, and on the bottom is the proportion that are depressed. And rearranging it, so if I bring this over to the other side, I get the probability someone is both worried and depressed is equal to worried given depressed times probability depressed. This may seem very abstract. Next class, I'll show you a different way that we can show this formula. And, oh, that's after our break. We got next week off. But that might bring that formula to life as to why it works as a formula. But it's a very powerful and useful formula. Okay? So with this one, I had depressed given worried. So among those that worry, what proportion are depressed? And you got the 151 out of 350. And again, dividing top and bottom by 583, I get the probability depressed and worried, like I had before. But on the bottom, I've got probability of being worried. So that's again very similar to what I had before. But look at this one. I've got depressed and worried is now probability depressed given worried times probability of worry. And I keep drawing attention, these two things match up. So I look at how many are depressed among those that are worried, and then I look at how many are worried. So I adjust for that bit. So I have two different ways of writing the same thing. That depressed and worried is depressed given worry, like I've got up there, or it's worry given depressed times probability of depressed. And we call this, no, this is chapter 9. That's on quiz 9. Test is not on, it's quiz 7 and 8. Not on the test. I wouldn't do that to you. So this I call my multiplication rule. That it's I can work out a probability of two things happening together by multiplying two other probabilities together. My addition rule is for an or statement, depressed or worried is equal to adding up some terms together. I call it my addition rule. So there are some special cases and the like within that, though. And, I've already got to that. So this probability, I should have boldfaced this. This is super important. This is a conditional probability. This is where everybody makes mistakes in interpreting probability. Most of the probabilities we encounter in practice are actually conditional probabilities. They're about two different things combined in some fashion. And and conditional probabilities are what is the hardest thing to understand. So what's the difference between saying among those that are worried, what proportion are depressed? And the statement among those that are depressed, what proportion are worried? I'm changing the sequence. That so we'll be getting into that in the next class. It's all about conditional probabilities, and most of classification is about conditional probabilities, about if you know this, what's the chance of that happening? That there is a special case, and again, there's another piece of jargon, and a lot of what we're doing today is just jargon and symbols that we use. I'm not expecting you to have a good deep understanding of it, and you may have seen some of it before, but we'll use this a lot when we come back after the break and to the next class on that'll focus on conditional probabilities. But suppose we've got a case. Oh no, I've got a typo here. I'm going to jump out of this and go right into my slides and fix it right there. Where did I do it? Nope. That was where I was. Excuse me. Bring my face back here. My typo. So I'm asking about a situation where we had, and I'll just type on my slide here so I can write this out. We found 36% of all students were depressed. Okay. But we found that among worried students, 43% are depressed. Okay. Numbers are different. So worried students are different from students in general. They're not exactly the same. If they were exactly the same, if there was no difference between those two groups, we would say that those two events, worry and depression, are independent of each other, that one does not impact the other. But if they're different, then knowing about one gives us insight about the other. I'll probably say this in the next slide. Yeah, see, I had this. So in this instance, we would say that they're not independent of each other, which is a very strange wording. That being worried and being depressed are not independent of one another. Independent is like saying not dependent, isn't it? It's like a negative. So not independent is like a double negative, not dependent. So should we be able to say that they're dependent? No. We try to avoid using that word, dependence, because dependence suggests there's causation. Being worried about grades makes you depressed, or being depressed makes you worry more about your grades. I don't know that. I'm not a psychologist. I've got no proof of that sort of thing. I might believe it, but that it's just what the data is showing. I'm just showing that in my data that there seems to be a pattern, that among depressed students that they seem to worry more. Among worried students there seems to be more depression. I'm seeing that type of behavior happen. That's all I'm seeing, and can really speak to that. So we've got that issue of causation versus correlation. I'm saying that the two things are correlated, but I'm not saying that there's a dependency here. But the language that's used is to say not independent, and many students find that awkward language. I do. Um, but you'll find in statistics, they do an awful lot of things that are in terms of negatives or double negatives, um, that they use in their language. It's very cumbersome and very confusing. And you'll see more when you take a stats course. The Why do we care about this? That in data mining, we're looking for cases where something helps tell us something else. We're looking for variables that help predict things. So we're looking at ones that are not independent, where these two numbers are quite different from each other. And the bigger the difference, the more useful it is for us. When the numbers end up being the same, it's saying it's of no help to me. And that if one of the questions on the survey had been, what's your shoe size? I don't know what size shoes you wear, what color are your eyes? And I was looking at, well, knowing the color of your eyes, if you've got blue eyes or brown eyes or green eyes or gray eyes, is the chance of being depressed higher or lower? Probably not. I don't think so. Anyway, I haven't heard about eye color and depression. Those things we would think of as being independent, that they are not related to each other. And so there are many problems where we like to go and see, is there any relationship between these two factors? And our hope is to find there isn't. Like researchers that are, if you were a company that made fertilizer or pesticides or whatever, and you want to know, is cancer more often the case when they use this pesticide? And you would like it to be, no, it's not more often, that they're independent of one another. Um, so we have a raging debate that's been going on for years about a chemical called glyphosate. It's used to kill plants. Uh, we use it in Nova Scotia on some of our forests to cut out the hardwoods. It kills leafy things, and so it allows pine trees and spruce trees to dominate that land. And but then there are many people that feel that it is a chemical that is harmful to our health, and it gets into our water supply, and it's dangerous. So different research studies. Some of them say they don't find any pattern, and other ones say that they do find a pattern. That the chemical companies want them to be independent. The other groups that are fighting it believe that they are not independent. There is a relationship present. They don't care if it's cause and effect. It's just a correlation is enough in that instance. There's one other piece of jargon, one I don't like. Many students get confused on what this is, but it does crop up, uh, and you may see it in a stats course or in a discussion of probability. And it's called mutually exclusive. And it's simple. It just means if two events are mutually exclusive, it means they cannot occur at the same time. You can't be worried and not worried. You're one or the other. You're yes or no. Those are mutually exclusive events. That if you go back to our table, the two columns in the table are mutually exclusive. You're in the W column or the not W column. In terms of the rows, you're in the ND row, the 1M row, or the D row. You're in one of those three rows. You can't be in two rows at once. But if I looked at being worried and depressed, no, you can be both worried and depressed. Those are not mutually exclusive. You can be one and the other at the same time. You can be both. So where a row and a column cross, we generally don't have that. We don't worry about that. They're not mutually exclusive. But if I'm trying to define categories for things, categories for a variable, I want mutually exclusive categories. I don't want to have categories that you can be in two of them at the same time. And unfortunately, we do have a number of cases where we do have that. When I was studying student data, if I was looking at the student's program, what degree are you studying? That arts or business or science or engineering can't do it because we have a modest number of students that are studying both arts and business or both arts and science. They're in two programs at once. So program, you could be in two programs at once. So program is not, those categories are not mutually exclusive. Until recently, we insisted that uh, almost everywhere that you were asked to fill out a form or something, you were asked for your gender and you had to identify as being male or female. You had to be in one group or the other. And we forced them into those two different categories. Now we've got, it's been accepted that gender is not a biological thing. It's more of a social thing. It's you define your gender, um, and you can define it the way you want to define it. So we could have male, female, other, but they as a catch-all. But if you want to get down to the other types of categories, um, we're getting people that may define themselves multiple ways. Even male, female, they may want to define themselves as being both. Um, how do we deal with that type of thing and come up with categories for studying gender as an issue? It's become very difficult. So the term mutually exclusive is not so much a probability issue, it's how do you organize categories? And we want them to be mutually exclusive. Don't get obsessed with it as a thing that happens in probabilities. Uh, and so, yeah, like rows and columns. Now, we have different types of ways of, I've just shown you a frequency table or a contingency table, but often you see it displayed as a probability table. And then it starts to get confusing that, that we may, um, it's a table that shows you generally joint probabilities. So if I go and I look at the table I had before, that that were frequencies. Oh, I don't have the table again. If I took all of the numbers and divided by 583. Now, we did do that with some. We did like chance of being depressed. We took the 207 divided by 583, and we got 36%. Or worried, it was 60%, 60%, that it was the 350 out of 583. That the if you take every number in the table, divide by the total in the bottom, you get these probabilities. This probability here, 21%, is the probability someone is worried but not depressed. We calculated this one, the 26% of being worried and depressed. 8% are not worried, and they're depressed only once per month on average. So these are all the joint probabilities of the two things happening together. This is percentage that are not depressed, that once per month, that are depressed. This is the percentage that worry. This is the percentage that don't worry. So the totals represent the probability of being in that row or the probability of being in that column. If you were doing this in a pivot table, then, and you did show values as a percentage of grand total, you'll get a thing that looks like a probability table. And it isn't unusual to see these, particularly in a stats course or a course that teaches about probability. Um, I don't use them often, and many students, when given this, if I asked you the question, oh, since I'm in PowerPoint, I can type on this. Suppose I ask you the question, what is the probability of being depressed given you worry? What's the deadline for Friday's test? Same as all the tests, it'll be Friday night at just before midnight Halifax time. And the quiz that you have on Saturday, that's on this sort of material, it's due Saturday night just before midnight. Anyone got any thoughts on what this probability would be? Probability of being depressed, given that you're someone that worries? And if you do it from the table that's here, how would I calculate it? You don't have to give me the exact number. Not quite. That you just told me your 26% is directly out of the table. That's the probability that you worry and are depressed. Both of those things. Okay? I'm saying that I'm only looking at those people that are worried. What proportion of them are depressed? We worked this one out before, I think. Oh, maybe. Yes, we did. I do have a formula for it. Oh, you're typing again. I'll wait till your answer comes up. Are you? Yes? No? Okay. Imagine my table that I've got there, and they aren't percentages. Okay? They're just numbers. I have 100 students. 60 of them worry, 40 of them don't worry. 36 are depressed, 44 not depressed, 21 are depressed once a month on average. 26 of the people out of this 100 are depressed and worry a lot, and so on. So just treat these as being frequencies. And I asked you, among those that worry, what proportion are depressed? What would your answer be? Any thoughts? Andy's typing. You can just express it as a fraction. Am I going to get something? 26 out of 60, exactly. 26 out of the 60 people. So it's You can imagine that if they're frequencies, and you can rationalize it in your head. And I've met very few students that can't do a probability question when I give them frequencies. So if I gave them the frequency table, asked them this question, that almost everybody would get it correct. But if I gave them this table here, I would have a whole bunch that would make mistakes like lamb made and so on. Those are very common. They get confused. And actually, if I really want to confuse you, I went into my table and I took this out and I wrote it like this. I have to fix this all up for my next class. Oops, I don't want that. And so I'm not going to do all the other ones, but you can see the pattern of what I'm doing. If I gave them to you as decimals instead of percentages, and so that this one down here would end up being 1.00, and and so on with all the others, if you can picture it, and asked you to do the same question. Um, I wouldn't necessarily get lots of students giving me 0.26 divided by 0.6. That these are probabilities. Probabilities should be expressed as a number between 0 and 1. Most of us have difficulty picturing decimals, that we can't see decimals. They're a very abstract type of number to look at. A percentage, we actually, many of us can imagine because we think of 100. And so 21% is 21 out of 100. And we think of, instead of when we see a percentage, particularly if there's no decimal portion to it, that we can think of this as a fraction. And fractions we're good at dealing with, not always manipulating fractions, but imagining fractions, seeing 1 out of 20 and those sorts of things. We can relate to that. We can't relate to decimals. That most have an awful lot of trouble dealing with that. And so uh, that I learned years ago, when teaching this sort of material to a couple of guys that were not among my best students. They seemed to be able to do very well on this on tests. And it was what they were doing was they changed everything that I ever gave them as probabilities. They changed them into physical counts and then made it all about frequencies. And once they had it in frequencies, they could do it. They could do anything. But probabilities were too abstract. I'm running out of time, so let me zip through the last couple of slides here. If you asked it to show in Excel percentage of row total, you've done that sort of thing. So you got 100% over here. What's that? This is a conditional probability. I'm looking at the probability that you worry given you're not depressed versus not worry given you're not depressed, or among those that are depressed. Look at this row here. That, whoops, excuse me. If can I do that? No, I can't. And I won't. I won't try fussing around with it. It wants to change other stuff. But if I'm looking across at this row, there I go. That is looking just at those that are depressed. What percentage worry and don't worry? Those are my conditional probabilities. So it's conditioning on the row that you're in. And you often don't see a table like this, though. Okay, it's what you get out of Excel if you do percentage of row total. And understand that those are conditional probabilities. Um, Many people don't like to report these because people misinterpret it. And this is the same way the other way. If I did it percentage of column total, and you were doing that comparing the 2019 to 2020 years, percentage of students that had different things. So this is among those that worry, what percentage are depressed. Among those that don't worry about their grades, what percentage are depressed. And you find, oh, it's much, much lower. So those that worry about grades seem to be, you know, have experiencing a lot more depression than those that don't worry about their grades. Maybe the two things are related. I don't know, but they behave differently. So there's a whole bunch of jargon. I'm running out of time. I'll be posting the slides. So there's a lot of it though, and all of these different sorts of words, and that the important ones have to do with conditional probability. It's the most important thing in probability. Everything else, I don't care if you remember. And there's some formulas. I'm not going to make you use formulas. Okay? I'm not going to have you go through all of this type of thing. You'll generally be given a table and you can reason it out of the table. And I think you should see that in any of the quiz questions that I ask you to find probabilities. You don't need formulas. Um, next class is coming up. So why is it important? It's because we're in data mining trying to predict an outcome given some information. It's really a conditional probability. So when I first looked at decision rules for classification that involved estimating a probability, that was estimating a conditional probability. And that maybe what we can learn about understanding conditional probabilities can give us other ideas on how to build models. And we will. Okay? The next class, I'm going to be looking at trees, which are a good way of exploring conditional probabilities. It's a way of making them more visual. And for many of us, that makes it easier to see. And a rule that's related to that that has to do with switching information from beginning. And again, that happens to come up in data mining, and it's the basis of a very popular tool for doing classification. Um, that and I'll get after you about, do you really understand what a conditional probability is? Because we make mistakes, a lot of them, to do with that. And so I'm out of time. So good luck on both Friday and Saturday with those. Get after me if you've got questions on things. Next week, we're off. We get a break, I guess. But it's the Remembrance Day week. And but I'll still be working on stuff. I'm just using it to catch up. You're probably trying to catch up on things as well. And but feel free to get in touch with me. And you guys take care. I may well post your next assignment sometime during the week. So you could start on it during the break week. I'll try to post it early next week. Okay, you take care. Um, enjoy your break. Bye now.